So I was going to talk to you guys a little bit about a community I've been working in for the last few years. It was not only called PyData, and I guess the name kind of took off after we worked in SciPy for many years, and SciPy didn't have as much catch fire outside the scientific computing world, and so once we switched to PyData, had an excuse to build a whole new set of tools, and also it kind of caught fire with a lot more people as far as like everyone uses data, people know what data is. Just a little bit about the organizations I work with. So Continuum Analytics is a startup out of Austin, Texas that does Python tools. I'm going to mostly talk about some of our ways we help industry, but also like our stack that we build on open source tools. Additionally, I work with NumFOCUS, which is an organization for advocacy of open science tools tools for scientists to build better codes and share their codes. And I think a lot of people in this SciPy movement came from the sciences and realized that if they want to also participate in writing code and writing papers, they have to like actually help and build up the tools a bit. So we actually work by one, having a large number of supportive projects, giving out fellowships to students who are more tools oriented, doing women in technology workshops, helping tools like Julia, for example, bring in money and help them support that effort of grant makings and whatnot. And then we have our own conference series called PyData, which you talked about a lot of these tools I want to talk about today. Just to give you a smattering of the different projects we support. You see things that were mentioned this morning, like Julia, Jupyter or IPython, NumPy, say software carpentry, things like that. The whole kind of journey for us really kind of started with NumPy, and so we often draw the same map this way as well, where NumPy has become the center of like our world as far as holding your data, and it becomes such a useful place for scientists who often have performant code in C or Fortran. And then they expose a NumPy interface, and then once you have that, you have access to a whole wide world of tools. So NumPy kind of fueled this whole kind of movement, and we also saw that it's also fueling a lot of people in industry. And here's a small smattering of clients that we've had who are using NumPy and asking us to speed it up for whatever reason. And I think that at some point someone told me like, how many Fortune 500 companies use you? And it's like, well, basically all of them now. So it's like, well, that's nice, but it's still kind of, where do you go for the future? Kind of our big picture, though, is really about empowering domain experts with high-level tools that kind of exploit modern hardware. So we have kind of, people who've gone from like wanting to do real field science, but also need to do real computation now, and helping them do that analysis in a high-level language. And we kind of always approach this from an array-oriented computing standpoint, where if you vectorize things just like you do in MATLAB or APL and things like that, you were able to realize the speed of your chips and actually vectorize. And as we move to modern hardware devices, so like for example, here's a GPU architecture that has all those little green dots being cores. You have a lot of cores that, in order to feed those correctly, you have to really have a lot of computation, and doing something outside of an array-oriented approach is very difficult. And on top, that's a Xeon chip that just shows how many, like the cores are starting to take over even there, and how much memory you have is much different space. But as we kind of like evolve, there's this whole kind of big data movement that's going on. I assume that it's happening in Asia as well. But so, I want to take an aside and talk a little bit about why big data and what it is, and then how do we evolve the tools that we had from that SciPy stack to a big data world and what that means. So for us, like the big thing is that big data is kind of a storage kind of disrupted the world. And so as we had hardware cost or hard drive costs go down, all of a sudden we can start to store all this data. And if you have the data, you might as well analyze it, right? And so now you have this kind of disruption where I've been able to store all my data. Now I have to build systems like Hadoop, and on top of that, Hive and HBase that are able to go through lots of pieces of data and transform it in a robust kind of way. And now you can actually do, like the first wave is just kind of basic analytics or statistics, i.e. like here's a word count or here's how many users click this button and things like that. But as we move on into the next phase and we've kind of established some of the Hadoop stack and some of the big data stack, we're starting to see much more complex analytics and preparing for that. But as with any kind of turbulent time, there's a lot of technologies that kind of come out of it. And here's what's called the Gartner hype curve. And so it basically starts by saying you have some technology trigger. So example, you had cheap storage or in Hadoop and ETL solutions. And then you have, my favorite part is the peak of inflated expectations. So there's technologies up here. For example, they have up here the complex event processing and social analytics space. Social analytics is definitely one of those places that companies are being sold for hundreds of billions of dollars, right? Maybe not that much, maybe tens of billions. But right after that, you enter the trough of disillusionment. And you see here, MapReduce is definitely coming down to the trough of disillusionment, then slope of insight, and then plateaus off here. And so kind of the point of these curves is to show like where a certain analyst thinks different technologies exist. And also show the plethora of technologies that exist there. I mean, for example, here's Internet of Things coming up. Now, this was 3 years ago, so Internet of Things has probably definitely moved up into the peak of inflated expectations. So 3 years ago, we saw this just huge number of places where big data could be used. And so coupled with the fact that you had cheaper ways to store things, cheaper ways to compute, and all these solutions coming out, there's just been kind of a whole world view of how do we actually change what we're doing in order to take advantage of all this stuff. And so I'm going to talk a little bit about where that kind of, what we're doing and continue to do some of that stuff. But first, this like kind of big data has always been around. It's just been of different sizes. Like whether in the past, scientists, and this is a 1950s, this is the SAGE radar survey for the US, and each one of these sites had different radar detectors, and they were pulling down quite a bit of data, and they had to build an entirely new system in order to process this data. Back then, it was 3.5 acres of floor space for each one of these environments, 60,000 vacuum tubes, which is quite a lot of glass if you've ever seen a vacuum tube. And then, like the one that grabs you is, we learned how to write things in very few lines of Julia this morning, but back then, 500 lines of assembly was kind of common, right? So this was a very big system. And now it was, so $10 billion, 1954, employed 20% of all programmers in the world. So like, not only, this system became the biggest employer of computers, so a lot of people learned how to do these sorts of things. But the kind of the kicker there is like, it was really very small amount of power compared to today's supercomputers on very low modems that had 32-bit, 1300 baud systems that kind of worked at a very small time space. And so back then, this was the biggest system possible, and it was just blowing people out of the water. And the way it kind of like broke down is you actually had this huge facility and kind of all these types of instruments just so you can get all the radar data that cover the US. So big data's been with us for a long time. We've built new systems in order to process it. Now we're able to make it so that everybody can kind of build these big systems and process a SAGE-like sort of size of data. We had the opportunity to work with DARPA and DARPA is a defense, in the US, is a defense research institute. They invented things like robotics and the internet and things like that kind of helped all of, they want to help generally the defense agency, but they generally spill out to help the whole world, right, sort of thing. And so one thing we worked with them is to kind of build our tools to go beyond the standard complexity of data today. And on one thing that they really highlighted out is that there's no one-size-fits-all end-to-end system that meets their analytic goals. So the first thing to kind of learn about big data is that, one, big data's been around for a long time. It's just been called different things and used by different people. But ultimately, it's about going beyond your current capabilities, and it's not a one-size-fits-all. So you do have to be able to answer enough questions about your data and your different systems in a way that is very flexible. And how do we build that flexibility? The Python has been a very good tool about building flexibility. So our viewpoint was we can actually extend the Python language, and then that'll help domain scientists also be able to test their hypothesis against data in a much more real manner. So before I get into kind of like what are the products we build, let's like look at some of the kind of, I guess, truths, if you will, or facts about some big data. The first thing is that like a lot of the data systems out there are aging. I think SAS is probably one of the #1 tools used, and it was built in 1970-ish. There's a lot of nice things built in the 70s. SAS, SPS are definitely one of those. And those are used by data scientists throughout the world. And so when you have a system that was built in almost 50 years ago, it becomes really challenging to keep it up to date with this changing landscape. Just like we saw with Julia this morning, talking about how different computing environments have a hard time with complex types and compilation of those complex types. Yeah, if you rebuild from the ground up. But at the same time, like the tools we use today are not new either. I mean, Python is 22 years old. I think that was a little bit shocking to me the first time I saw it. Python's older than Java, which for all the things, they got a lot of things right that Java didn't get right, and you just kind of wonder, why did Java get all these things wrong that we got right when Python was already out? But then NumPy itself is only like 8 or 9 years old. And so the tools that we're using today often are, half the age of the industrial players, and they're kind of coming of age right now. But then there's the next wave of tools that handle very large data and whatnot. The next kind of truth of data is that there's the fundamental physics of copying data is much more expensive than computation. It's just kind of true for like different worlds of expensive, whether it's your electrical power and cooling, time, or even like human factors of keeping that data correct and the same and having provenance between data. So as data piles up, it becomes very hard to move it and change how you're processing it. So getting something that's flexible up front is very important for your environment. With that said, it's also true inside a single computer for moving your data from your memory to your CPU. That's actually much more expensive than just recomputing sometimes. So everywhere you look up and down the stack, moving data has become more and more expensive. So we have to come up with better ways of interacting with the data on the system that exists, or doing I guess what they call edge computing, where you only bring in good data, not bad data sometimes. To kind of drive this point home, I just have a couple of slides that show what people who know about large processing systems show you when they say, this is my processing system. And you can't really read the slide on this thing here, but you kind of go through several layers of ETL and processing till you get to some analytics, and then you turn that analytics thing into some publishing thing that then is on top of that you have governance and a whole bunch of tools. And so this is what you kind of look at, and this is from Stephen Urbanek, who does Data Academy. And it's a huge process inside the business just to manage where your data goes. For scientists, it's not easier. It's just they kind of forget about a lot of the effects. And so here's one flow chart from a paper on like the scientific workflow of data. I think this came from the Viz Trails, which is a Providence Manager tool. And even here, you go through lots of steps of iterating on your data to probably do some big computation and then go to a result. And then you also have a lot of side processes as well. So these processes are pretty difficult to kind of replicate and figure out. So anything that makes that simpler and you don't have to set up all these processes is actually quite much nicer. People are really gravitating towards that. There's even this concept you can find on the interwebs, as it is, of data having mass. And here's a nice kind of picture of you have data services with latency to data, and apps that need some throughput to your data. And as your data grows, these things have to serve towards that data. And if you really want to get crazy, there's this guy, datagravity.org, that gives you a true physics equation modeled after something that looks like Newton's first law. He even has a picture version with data times applications times number of requests and so on and so forth. So the world has gone crazy about moving data on the day with gravity. So data matters. It's getting bigger. Moving it's harder. But then the other kind of big point we have to make is that memory matters a lot too. Feeding your CPU for complex analytics is a difficult process. And so where 1980s, you really had just a single CPU with some main memory and some mechanical disk. It was a very simple system that everyone kind of managed themselves. Today, you have 3 levels of caches probably, typically a main memory. Often, you'll have some solid state disk. And usually systems I build, you're going to have you're going to have another mechanical disk that usually has a RAID array and some mixed with some solid state into that as well. So the memory hierarchy has changed quite a bit in the last 30 years. And I think that it's something where, at the most part, most people still kind of work in this 1980s approach of, I'm just going to pull things from memory and I'm not going to worry about caches and things like that. And so now you have kind of the gambit of how do I actually manage memory coming in as well as memory, as all this data moving. And the final kind of bit of truths, if you will, is that how much speed matters. And so here, if you take these black boxes, so the one black box being a nanosecond, and you can see your L1 cache reference is basically a nanosecond. And then these blue boxes are 100 nanoseconds. So this is one main memory reference. So going from main memory to cache is already 100x already. And so then you look at here, if I want to just compress with a fast compressor, Zippy for example, you can see here I have now 2,000 times more than just actually hitting my memory. And then you have at the other end of this, so in blue is about, it disappeared up here, but it's about 2,000, about half a nanosecond, and this red is 1,000 bytes read from a SSD. So you can see here 200,000 times difference between this guy over here, which is just a cache read, to actually reading that SSD, which is already a fast read. And then you see, if I have API calls and I have data coming from different places, all of a sudden the amount of time it takes to get data back from somebody is a lot of time in that one block. And so being able to know where your pieces hit and where your actual, how performant your algorithm needs to be, whether it can hide inside this kind of packet round trip or if it has to come up at this very low end of the speed is something data scientists have to manage throughout their life. So performance becomes a major vector in your, key impactor of a lot of the data systems we build. So in that regard, going back, this leads us to what we actually call the data science dilemma, which you have massive data to deal with, you have tons of tools, modern hardware that becomes harder to use, but at the end of the day, it's had a huge impact on company bottom line. I think many people, I think a lot of people in the big data world are looking at big data as a way for IT to stop being a cost center and to be a money center, a profit center of the businesses. And so that promise, we're willing to put up with all these really hard parts of the ecosystem in order to get a much better bottom line, whether it's from financial or engineering or marketing and so on. And so why Python in this world? So with all this complexity coming on and Python being considered relatively a slow language, why do we use it? And we like to give the spectrum from the occasional user all the way to the hardcore developer. So the occasional user can cut and paste and modify a few variables and their code works really well. And then the developer is kind of your CS grad who knows multiple languages, can build compilers and databases and things like that. And on both ends of the spectrums, Python fits in, and there's a place for people in the Python world. Now, for data scientists, they kind of fit in the middle, where they have to code every day, and they have to interact with low-level code, but they don't always need to write that. They need to actually try out new ideas. And so you often extend frameworks, build new objects, wrap your code, or interact with like a domain expert such as like an engineer or a quantitative finance person. So this is, we claim, is a unique aspect of Python, being able to go from both sides, being a very general language, being also a very specialized language when you need it to be. So that's why we have inherited Python as our view. So a little bit about like continuous view inside this ecosystem. So for us, data exploration is the central task, and we believe, visualization, and I'll show some of our visualization tools, is our first-class citizen. I think you get more bang for your buck by just looking at your data and being able to explore your data than you do applying 1,000 models on it right from the start. So just getting a notion of what your data looks like, how it looks, and that sort of thing. And then the big thing for us is just enable agility so data scientists can use their tools. And I'll go a little bit through some of these, but we have kind of 3 different types of systems. We built the environment, so if you use, how many people use Anaconda in the room? Okay, so that wasn't everybody, so definitely if you ever had trouble installing Python, go check out Anaconda. Anaconda installs the entire stack of the SciPy tool sets and LLVM and things like that, and links it up in a nice way. And so Anaconda is kind of the thing that a lot of people kind of come to us, is just how do we build our systems. Then we have like analytic systems. For example, I'll talk a little bit more about these. Blaze, which hooks up to a lot of different databases and data sources, and Numba, which is kind of Julia inside Python, if you will. So an LLVM JIT compiler. And then we have a visualization system called Bouquet, which is quite nice, and I'll show it. So our position is basically no one-size-fits-all point-and-click application is ever enough to solve business problems, and so we believe a language-based platform is needed, and that has to be powerful enough that it can do pretty much anything, but also accessible to domain experts. And Python is a nice language for doing that, and so that's why we kind of have pushed so far on making Python a better place to be doing data science. In that, we have kind of a data exploration platform for the enterprise called Vocari. And so what Vocari basically is trying to help businesses take their expertise to either their computers or the cloud, or however they'd like to do their computation. If you think of it this way, I think this is a very popular viewpoint of data science, where you go from data acquisition, preparation, data analysis, and then interpretation. The kind of our platform, we use Blaze for our data acquisition piece. We have data preparation through our Anaconda server and the number of Anaconda tools that are available. I think we have 200 different tools from the Python ecosystem. And then analysis, we actually love the IPython notebook, or Jupyter notebook, so you can use your Julia kernels as well. We see this in business after business, where you just get data scientists together and around the IPython notebook. There's 2 things you take away from my talk. Go check out Anaconda, go check out IPython notebook. Those are really tools that we use every day. And then finally, we have Bouquet, which is our graphics interface that I'll show in a bit. So just show Anaconda, once again, easy to install. It comes by default with 100 libraries in it, but it has, I think, it doesn't have everything that PyPI has it, but it has probably up to 1,000 libraries kind of built in that you can install. But it also interoperates with PyPI pretty well. And so it's a platform that's kind of taken off, and a lot of people use Python through Anaconda these days. We actually speed it up if you need things to be faster than Python. We have optimized libraries. We also have a commercial version if you want to bring your binaries inside your firewalls and that sort of thing, that we can help with that. We have anaconda.org. It used to be binstar.org, but now we've changed the name to anaconda.org, and here you can upload your packages so anybody can use them. And so it just takes your binaries, and when you install Anaconda, you just supply a command line argument, and it grabs it off of just like a GitHub kind of thing, except for your binary packages. Vocari, I talked a little bit about, is the kind of the unified system of using IPython on the cloud or inside your on-prem environments. And there's the enterprise version, which is effectively something that you can do for on-prem that businesses will bring in so they can share inside their own intranets. So those are kind of like that's kind of continuous view. That's people often ask me, how do I make money? It's off those tools. So I want to talk a little bit more about like the tools that we're building to help build a better data ecosystem. And these are kind of tools that once you start using Python for a while, you realize that you still have to use a number of tools to get to big data. And it becomes a bit of a pain when your NumPy array doesn't fit in memory anymore. Your pandas data frame kind of, you get outside the range it can hit with its compressed memory backends and things like that. And so what we want to do is help build tools that make it easier for people to get into doing data analytics and keep on doing it for not only the part-time, but also the business user as well. And so we have I'm going to talk about 3 technologies that we've built that are open source. Anyone can download, use them, distribute them however you like. Blaze, which basically is a way to map arrays and compute services to break down different data silos. And so you can do data blending and also join different data sets and things like that. Very handy tool for a single interface for a lot of these systems. Bouquet, which I mentioned a little bit, was interactive visualization tool in the browser for Python. There's some other languages, but basically the idea of taking large data and creating interactive, rich data environments from just a small Python code. And then we have Numba, which is the optimizing compiler for a subset of Python, which has like multi-threading, multi-core, and GPU support. And so that's kind of the whole thing there is like, I get my data in, I can speed my data up, and I can visualize my data very quickly. So to kind of talk about Blaze first, Blaze kind of came out of this view of like what I like to call data pain, where you have hundreds of data formats. Your basic programs pretty much all expect it to fit in memory. Most programs have this viewpoint of like your world is just memory, and that if you run out of memory, they kind of don't really handle that well. And the other kind of side of that is like, so now you have to deal with how do you feed data into your kind of programs or write programs so that you can write them in chunks and create pipelines that also change quite a bit. And so I think that another one that Blaze isn't quite as solving, but this whole idea of configure your system and your parallelized analysis, those are kind of still open. I believe that Blaze has kind of hit those top 3 pretty well of like building new pipelines and whatnot. Now we're working on, building systems that are very easy to configure and also parallelized. But that's been what people have been promising forever. So the idea of Blaze is just like every tool. When you have something you need to do, you pick a tool based upon that need, and it has like some capability. So for example, here, when I want to hammer in a nail into wood, I use a hammer that has a nice fitted to my hand, but also hits that nail. And a lot of people try to use the, when you have a hammer, everything's a nail. It doesn't always work. But if you look at the problem a little more deeply, you have something that fits the problem and something that fits the person. And when you look at this is generally true of pretty much all carpenter tools, and there's a lot of different tools in a carpenter's tool chest. And so if you have all these kind of tools and they all fit your hand differently or in different ways, how do you build a system that makes it so easy for people to just pick up the tool they need and keep on going without having to understand how to use every one of these tools in an expert fashion? One kind of analysis for this is the Dremel tool. I don't know if this is popular here in Taiwan, but it's a tool that has tons of little attachments to it and a single kind of interface that you can just plug in your tool. And that's kind of how Blaze works. Blaze has a single API that hits a whole bunch of different data services and can compute on those ideas. For us, Blaze kind of hits these kind of 4 different systems. Coming traditionally from a scientific stack where you have things like HDF5 and B calls and MPI and things like that, to a world of like statistics and machine learning where you have pandas and Theano and scikit-learn. And those kind of like Python's been playing really well in those systems for a long time. Now in the business world you have the BI tools which interact with databases and typically have some interactive, like once you have a SQL query you have tons of BI tools that give click and point and click systems for lots of analysts. And so you need some interface to act with these BI tools, but you also need to work on a distributed system. And we often work with Impala or Spark or other tools like that. And so Blaze is a way for us to build programs that can interact with all these things seamlessly. And the way we do that is that we have kind of what I like to call the Blaze Triforce for all the Zelda fans out there, where we basically take data storage as a first class, where you can take any data object and pipe it into a computational backend via some abstract expression. So if I want to join two data sources and do some computation, I can stream it into pandas possibly, or just use Spark in a distributed environment. And to kind of drive it, so the idea being any abstract expression I can build, I can then attach any data storage to that abstraction and a computational backend and produce the kind of the analytics I want. The way this architecture is built is we have an API that touches this deferred expression and the data a little bit. And underneath the hood, we have a whole bunch of interpreters that's built on this multi-dispatching system. So adding a new interpreter is fairly simple. You just add your types to it and it recomputes and so on. And then we have a compute engine, which hopefully the user never has to touch. And we've had some success here as people have found that as Spark has changed, they've been using our tool and they found that some of the things that changed in the downstream tool didn't affect them because our API was a little bit more stable. To give an example, here's us building if I want to count all the web links, we have a data source that is basically the hypergraph of the Common Crawl, which is the largest public crawl in the internet, and so here you build your expressions with a few symbols, and we call them table symbols, which we give them some names, like a name and a node ID, and then the arc table, which is a node in and a node out, and we build a join expression where we join those two tables, and then we can do a computed, a split by, a group by operation here, where then you count all the node IDs joined. So I want to count all the links coming into the node, for example. Here's a bit where, so this is building my expression here, and now this code is independent of my data, other than I have to map data to these symbols. And that's what this data load does, and I'll show that in the next slide. And the nice bit of here is that I can use it with different systems very quickly. And then at the end, like you add into the compute system. In this case, I think it just uses pandas by default if it can, or Spark. Depends on how you load the data actually, because it'll look at how is your data loaded, and then I'll figure out if I can use that system or if I have to use a temporary store with another system. And here we can just, like, for example, pull out degrees based upon just kind of a dictionary mapper. And so looks very, kind of some magic happens here where you actually have to load the data. And what does that look like? So for this particular example, if I was using Spark plus HDFS, all I would do is create my Spark instance, read in all the text files, do a few maps to actually get them in the right form. So here's my index that actually splits the file and then maps it the two pieces and calling one an int, one string an int. And there's the arc file doing the same thing, but both pieces are ints. Here's the pandas system, just using local disk, where you do more of a traditional open and you create a data frame. And so we create two data frames. And so now we had a system where we go back and forth, where this same code can either drive a cluster running through, I think this was 10 terabytes of data, or running through a local piece of it. This is only like 4 or 5, I think it was 40 gigs or something. And so this becomes a very simple system for testing out your code on local kind of environments and then pushing the same idea to your production environment. As we kind of built out the system, we learned there's a lot of little things that you just couldn't do sometimes in some of these systems. For example, if I have a distributed array, there's still not a very good notion of a distributed array in a lot of the ACFS systems and a lot of the Hadoop systems. So we built this thing called Dask, which is kind of a DAG plus tasks, and we built different types of collections. So you can have an array or a bag of data. So an array being having slicing operations and orderings, into a bag being just like data that's unordered and just kind of inside this collection, like an unordered set. And then a data frame, which is kind of come from the R world. And so from that, you can do computations and the same symbolic algebrations on this kind of data interface. It creates a graph that can then be distributed out to any number of schedulers. And so Dask is kind of a tool that a lot of people have been able to use. I think where it's gotten a lot of interest is creating out of core arrays that then go to some multi-processing back into it. So being able to chunk from the several files and whatnot. So that became kind of a nice system when it's just outside of just your data system and you actually want to do some real computation. Here's an array. We pulled it from a Blaze expression, but then we figured out what we're actually computing on it through that through the adding and subtracting and algebraic functions. And then kind of a final piece in the Blaze family is this thing called Odo, which is named after a Star Trek character who's kind of shape-shifting. But Odo, every node on this graph is a data format, and every line is a converter, and the weight of the line is given to give the speed of that converter. So using the same sort of kind of multi-dispatch trick, I can figure out how to go from this graph. If you go to the website, it's easier to read, I guess. But going for something like, for example, HDF5 all the way to a TSV type file or something, it can manipulate itself through this graph and figure out the best way to get from one format to the other. I think this kind of came out of our need of seeing everybody just giving us dumps of different formats and making us figure that out. And so it's very simple, Odo from the source to the target. And here's an example of pulling things into a pandas data frame and then throwing it back out to a Hive database. And so that was kind of like the Blaze ecosystem. I'm running short on time, so I'll probably speed through a few more of these. So Numba is another project that we use quite a bit. It's just-in-time dynamic compiler for Python, and it's basically compatible. So it's basically kind of NumPy compiled down to LLVM systems. And since NumPy already gave a rich type system that tells you how to declare a lot of arrays, there's a realization using some of the best kind of compiler technology out there with the LLVM tool stack, you're going to get a big bang for your buck. To kind of show you a little bit how that works, and sorry, this is really small, but basically you have a 2D sum, which is just a couple of for loops here, and you have like a little function that's AutoJIT on it. It actually will produce a intermediate C language IR, for example here, which then gets piped to LLVM. And then from that, we're actually able to interface with, for example, CUDA through PTX or different ARM or x86 compiled like low-level languages. And so LLVM became a way for us to interoperate with a whole bunch of different types of codes in a very performant way. To show kind of like our performance, which is hard to know what all that means. Here's Numba kind of vectorizing a Mandelbrot set. So you have kind of your typical picking your Mandelbrot set, and here's going through all your iterations to see at what point do you reach the Z reach 2, and thus escape the space. But we can also use vectorize, where sometimes we don't know exactly what the type is, or because the type inference doesn't work well. You can always give it a type. So here's a type signature, and then target for this example is like, hey, target the GPU, and we can see here kind of speeding up from straight Python to a CPU, a Numba CPU being 100x and a GPU being like 15,000x for timing just like other latencies and things taken off the picture. So that's Numba. It makes a lot of code, NumPy code, a lot faster. And then kind of our final thrust in helping the ecosystem is through data visualization. And if you look at kind of your standard data visualizations, is you have like some presentation that needs some static data plot in Matplotlib and Chaco, and there's a lot of good tools for doing that. But as you move into big data, you can't really put all your data into a single image. You really need some way to like interactively view it. And so you need to have this large data set, and you also like want to see a lot of different kind of graphics. And so we built this tool called Bouquet. Bouquet starts off as a Python library and then generates generates a JavaScript backend, and so there's bouquet.js if you're a JavaScript person. And we generate a whole bunch of different types of plots. And if you go to bouquet.pyday.org, you can see a huge gallery of them. But it has some of these kind of features here where it's interactive visualizations right from the get-go, and you have streaming. You can set up servers to have streaming dynamic data sets, all written from Python without any JavaScript. It used to be you never could write JavaScript. Now you can actually add little JavaScript callbacks. And because everybody loves it, we added matplotlib capabilities as well, and compatibilities. Just to give you kind of a view, if you go whip up an example, like the first thing you get is, let me see, this isn't, well, so that you have tools such as panning and zooming. I'll just go, let me see. Well, so I guess in this data set, for example, you can pan and zoom right off the bat no matter where you're at from a static website. But you also see faceting, for example, being able to color by the dot, and also the opacity showing different pieces there. And so you get a lot of the visual assets very quickly. Then here's an example of building widgets. And so if you go to the website and look at the Apple stock or the stock ticker, you can kind of start picking off different stocks, and you can see a whole bunch of different widgets that will update and then tick through, and also build different widgets and sliders and things all from a Python script. Here's an example of a cross filter where you can load up a data set and then pull different aspects of that data set into X bar, Y bar, and look at a whole data set back and forth. I believe this one is years of cars, and so you can see kind of the different distributions on each one of those axes, and also the comparison through the years, for example. And so there's kind of some really nice interactive things there. Here's an example of an ocean viewer where we were able to take all of NASA's ocean data and create sliders that slice this data back and forth and present it only the data you need in your browser and downsample correctly. And so this is a technique that we often call abstract rendering, but it's a downsampling that has some complex analytics inside of it, such as doing fancier joins or fancier like per capita. I think a common one is when you show a map, you have to be very careful not to show just population and showing per capita densities and things like that. And once again, there's no JavaScript. Literally, it's 3 or 4 lines of code to produce a fairly complex map. And on this one, you can actually, if you go to the website, you'll see that there's hover plots and things like that. Let me see. These slides are. Let me go and show you some of the bouquet tools. Okay. So, yeah. So to show off, so if you go to the gallery, there's a very small number of code. And then of course my JavaScript takes over. And so you see here you have a very small amount of Python, but I'm just coloring by figure, and I have a whole bunch of different attributes. Oh, okay, sorry. Thanks. So for this particular code here, it's a pretty small amount of Python that you can generate and give a whole bunch of, there's a set of T-Vault tools, but all I'm saying is scatter on a bunch of different points, and then I can change the radius on a vectorized format, and then I open up a browser. And because this browser is really small, I'm having JavaScript problems, of course. And so here's, for example, a zoom into this thing and things like that. So if I go, so if you come here, you can see a whole bunch of different gallery options. One I do like this one of Texas, which highlights the hover tool quite nicely, and all these are static plots, and so you get hover tools very quickly. And so if you're showing government data, if you have a file that shows where the geography is, you can do some cool things with that. So at the end of the day, we have a lot of tools that are being created, and we actually usually talk about it being big data being kind of like a Cambrian era where lots of different pieces of life were created. And so the PyData ecosystem is really kind of in that stage of being able to blow up and help the world understand their data in a much more real way. And I think that a lot of people, if you look out there, the data science world, a lot of people loved Python. They just needed to be expanded to these very large data systems, which are traditionally dominated by Java and SAS and things like that. And so that's kind of a little bit about what we're doing to help kind of work in that era and help the exploration of the data world. So thank you very much for your attention.
We can take several questions.
So I have a quick question. So Bouquet, my understanding was that it used JSON as the transport protocol. This seems like an odd choice in the context of big data because it's a kind of a verbose protocol. I mean, have you thought about binary protocols or
I guess the question is why use JSON for and why not a binary protocol? So essentially it comes down to JSON is just the de facto thing in the internet. And to be serviceable to a larger number of APIs and whatnot, we're just using JSON for the backends. There's no reason you couldn't use a better binary blobs. I think like Seaboard is a nice system out there, and there's a few others. But it's kind of like, if you have your own reader that can read me data and you can actually put that into the JavaScript, then you can actually load it however you want if you give us the array. So you can actually hook up underneath Bouquet to fancier formats. You just have to know the JavaScript a little bit better. Our kind of view, though, is that only move the data, like do all your computation on the back and only move data that you need to the browser that you do. And so while we're able to view lots of big data, we don't pipe it all to the browser. We try to push as much to the Python tools as possible, and then only stream as little as we need to actually to that viewport. So in the end, if you have really big data that has to go to the browser, yeah, you can build better systems with Bouquet, but Bouquet out of the box is more piping only the data you need at the time you need it.
Any questions?
I want to give you a quick comment. So thanks very much for building such a great tools and also PyData community. So I'm one of the organizers of the PyData Tokyo meetup, and
cool.
The community is now we have more than 700 members now, even though we started last year, and in Japan there are a lot of people are interested in using PyData tools now, and so I hope that a lot of communities in Asia will contribute more to build a more great community, PyData community in the future, and I want to be a part of it. I mean, the PyData Tokyo.
So I think one thing we've kind of developed PyData as a kind of a brand to give away, and lots of people using it. We were actually running conferences in like 2 in Europe this summer, and I think Berlin happened like 2 weeks ago. London's happening like in a week or two, and then we have like 3 or 4 in the U.S. But I think that there is an opportunity if there's a local group that's interested in running a PyData conference, helping those groups organize and get sponsors and things like that. I think having a PyData Tokyo would be a wonderful idea. I do know that there's some work being done to have a PyData Shanghai, but who knows? It's kind of one of these things like you need both the people who are logistically there available who can help you drive it, but there's a large selection of people who work in this ecosystem that we can help bring in for sure. So definitely get in touch with me, and if we can make more PyData Asia happen, that would be amazing.
So the time is up. So let's thank Dr. Terrel again.